Good morning, everybody. I'm Thomas. I'm the GraalVM project lead, and I'm the founder of GraalVM. And today I will talk about how we maximize performance, or how you can maximize performance with GraalVM virtual machine. I will keep the introduction relatively short because I think many people already heard about GraalVM, and I don't want to bore you. And then I will have some live demos, some more detailed information on how a compiler is optimizing your program. We'll show some compiler graphs, some assembly, so get ready also for some really low-level stuff. And then I will talk a little bit more like what are practical implications for you when you write your programs in terms of like what you should do to get the maximum performance out of them. Right, that's our safe harbor statement. There is one extra safe harbor statement on there, which is new, which is for GraalVM native image, which is currently in early adopter status, but is still ready for production use. All right, so the idea behind GraalVM, what was the idea behind it? We started this as a small research project, a really very academic research project about 8 years ago, where the idea was like, oh, let's build one virtual machine that can run many languages. And not just Java-based languages like Scala, Kotlin, etc., but also dynamic languages like JavaScript, Python, Ruby, etc. And so this is really our ambition with the GraalVM project. GraalVM should be the universal virtual machine, and we think that it will, in the future, be everywhere in your cloud stack, running programs, not just JVM-based programs, but also Python, JavaScript programs, and others. And these are really the two main goals of the GraalVM project. One is run programs more efficiently, just make them run faster, with less memory, with better startup. And the second goal is to make developers more productive in the sense that we want developers to choose the language they like, and not care about, well, what's the actual performance of that language, etc., etc. So we want to give you a way to run your programs and to write your programs also with high-level abstractions that is enabling you to like code faster, and the underlying virtual machine should make those abstractions performant. The part that is most common to Java programmers about GraalVM is that GraalVM can run any JVM-based language, and it can run these type of languages in the context of OpenJDK. So this is what we call also the GraalVM just-in-time compiled mode, where we run GraalVM in the context of OpenJDK. It can run here on the Java platform also other languages, Ruby, Python, R, and JavaScript, including Node.js. And we can run static languages also on this platform with C, Rust, C++. Running on the OpenJDK platform is one of the execution modes of GraalVM. Another one is that we can run on the Node.js platform. So you can run Node.js applications and use these languages. You can run inside the Oracle database. We have a prototype for that as well, to run your stored procedures with GraalVM. And you can run standalone. This is what is commonly known as GraalVM native image or GraalVM AOT mode. The more detailed project goals, a little bit more detailed laid out, is first, high performance for abstractions in any language. That's goal number one. Goal number two is low footprint and ahead of time compiled mode for JVM-based languages. This is the native image part. Number three is to have these languages not just all run on GraalVM, but also play together nicely, so you can use language interoperability between them. And goal number four is to allow the GraalVM virtual machine to be embedded in other platforms and programs, like the Oracle database, or like Node.js, or any runtime you like. We also have at Oracle a big SaaS application called NetSuite, who are embedding GraalVM in their SaaS application to make it extensible. In this talk today, I will focus about the first two parts. The first part will be to show how we achieve the high performance for abstractions in any language. And the second part will be on AOT and footprint reduction. This will be covered in this talk. Point number three, if you're interested in that, there is another talk today by Roberto Cortes from TalkDesk, how he's using the polyglot capabilities of GraalVM to write polyglot applications. But I will not touch on this today. GraalVM comes in 2 editions. There's a community edition that is open source on GitHub. You can use it for production. There's no restrictions on it. And there is the GraalVM Enterprise Edition, which is an Oracle product that comes with support, but that requires a license. Except, of course, if you run it on the Oracle Cloud, where it is available for free for you. And the Oracle Cloud also has now a free tier, so you can have a certain amount of machines for free in the Oracle Cloud, running also your GraalVM enterprise applications. We maintain a lot of code open source on GitHub. We maintain 3.6 million lines of code is maintained by my team open source on GitHub. This is approximately the distribution. The numbers are not very detailed, but you can get a feeling of how complex the parts are. We maintain code bases for the languages that we implemented on GraalVM, JavaScript, Ruby, or Python in separate repositories. And then we have the core repository with the compiler, the substrate, which is the native image virtual machine. And we have Visual VM as well on GitHub. And if you're interested in any of those parts, feel free to check out our GitHub repositories. There's documentation up there. So let's go to the first part, high performance for abstractions in any language. And I want to show you a little tweet that I had an exchange a couple of weeks ago with a Java performance expert that I very much respect, Chris Newland. He wrote also some books on Java performance. And he said, in the end of this exchange, we were discussing well, how do you write code that has to be performing fast? And his answer was, well, I tell my developers that hot code should look like it was written by my 9-year-old. No functional programming, no advanced object orientation, just very simple things. And this type of statement is probably true if you have not a very good compiler and runtime underneath. But we in the GraalVM project, we think we want to make in the future this statement less relevant, because our vision in the GraalVM project is that you can use these high-level abstractions and you can use these advanced features, but don't have any performance regret. And GraalVM as a compiler is already farther ahead than other compilers in this field. I will show an example of that right now in the demo. But we are this is not just about now, we want to also in the future be even better on these high-level code abstractions. Because you, as a programmer, should really, you should not worry about how this is in the end translated to the hardware. This should be transparent to you. You should focus on the logic of your program and use these nice abstractions, which often makes you faster and more productive as a programmer. So for this, I have a little demo here. Let's go here over to some source code. So the demo program I have here is, I have here a program that calculates the hash code of an object, or a hash code of 2 values, an int value and a double value. And this will be the raw version of how you would program this manually. But in Java, in the newer Java versions, you have a utility function, and I've copied it here just so you see it on the screen right now. But usually you would write here objects.hash. So this is that utility function, and this utility function will give you it takes a variable number of arguments, and it will iterate over those arguments and then call the hash code on it. So this type of function is available in the library, but when you now use this function, and I have here a little performance test, and I'm using here the latest Java 13 to run this. So I'm running this with the Java micro benchmark harness, and now we are running here the abstracted version of this code, the version that takes those two values and passes it to this abstract piece of code that calculates the hash code. And we see that when we run this on Java 13, we get a big performance hit for using this abstraction, because the raw version of the method is going with around 460 operations per microsecond, and the abstracted version only 110. So for using here this loop abstraction for like this more general way to calculate the hash code, I'm taking a performance hit of a factor of 4. And I have here disabled Turbo Boost on my laptop to make sure that the numbers are more appropriate. And what I can do now as well is I can run this. I have another Java running here, which is the graalvm distribution. This is I'm running a Java minus version, and what I've done is I've set the Java home directory to the graalvm community edition home directory. This is actually everything you need to do to just use graalvm. Just change your Java home directory to the graalvm home directory, and it works out of the box. And what I can do then is run this with graal, just with the graalvm community edition. And we see that even the abstracted version provides the high performance. So even if you use this abstraction, Graal is able to make the code so efficient and the same efficiency like your raw version. It's actually exactly the same performance. And we will now look into the white box, like we will treat the compiler as a white box and look into what it does, so you can see how Graal achieves that. So this piece of code executes the same speed as this piece of code. There's quite a lot in there, and in order for you to get a feeling of what the compiler does with this piece of code, I've created various versions of it in pseudocode of the transformative steps that the compiler takes when it creates machine code from this method. So this is just initial version. So initial version is just my abstracted method, and it calls that hash function. This is the initial version, just rewritten a little bit to account for the fact that this is how it actually looks in Java bytecodes. This is hidden for you in Java source code, but in Java bytecodes, because this is a variable argument function, it will create a new object array, it will box the functions, and it will call the original function. This is just the Java bytecodes expanded. This is what the compiler sees when it sees that method. One of the first things the compiler does when it sees the method, it does inlining. So it will take the contents of this hash method, and it will just inline it into this method. We can already see after inlining here that there is one statement even underlined in your IDE, which is, oh, this is dead code. Right? After I inlined this hash function, this general purpose hash function, into my original function, then I can remove some dead code. I can remove one check. I can remove the check that array is null, because array is newly allocated, so it cannot be null here. So the compiler can simply do that. It's not a problem. The next step of the compiler here is to replace the multiplication by 31 by a little trick. It is just replacing it with a shift left by 5, and then subtracting the same value again, because this is faster on current hardware. So the compiler does a small trick that is just, instead of multiplying by 31, it multiplies by 32 and subtracts the value again. Minor optimization, but it's still another couple percentage faster. Next step the Graal compiler does in this code is it unrolls the loop, because we have here a loop over an array, and the array has 2 elements. So all of this is constant. So instead of making the loop, the compiler will just copy the loop body 2 times and remove the loop. So this is now the new version of the code. after this version 6, we go to version 7, where after I unroll this, now I can do escape analysis on the original array. So escape analysis is removing object allocations. Because the compiler sees this object allocation on the array, the object is not stored anywhere. It's only used locally. So instead of actually allocating the object, the virtual machine will only simulate the object. It will only simulate to have the object around, and it will replace every access to that array, in this case, with that original value. And some of the accesses now fold as well. So this check is folding at the same time because I don't know that at this position in the array, the value is never null. So this is now version 7 of that code, where I have the boxes of those two values and I call hash code on them. Version 8 now is inlining the boxing of the integer field, the hash code function of the integer field, because I'm boxing the integer field and I'm calling hash code on it, and the hash code of an integer is just the integer value itself. So instead of boxing and allocating the integer, I can do escape analysis here as well and avoid that allocation. So I can just use that int value. I can do a similar thing for the double value, but I can again remove the boxing because the box is only used locally. And I will remain with a function called double.hashcode. Double.hashcode is an interesting function where it will go to double to long bits, and double to long bits is actually a kind of complex method in the JDK. The reason why it's so complex is that it has to check for the not a number value of double, and you can have different bits representing not a number, and we want all not a number values to have the same hash code. This is why this method is written in the JDK like this. So this is the method to get the hash code from a double. It is checking some bits and then returning the temp. The interesting thing here is that on modern hardware, this is actually not the most efficient way to code it because we just want to check for not a number. And here we need multiple conditions for that. We need multiple branches for that. And that is not the most efficient way on a modern hardware to write it, which is why the compiler in this scenario now does one more optimization to this piece of code, which is to undo the optimization that was done in the OpenJDK and turn back to a more reasonable way to program this, and it looks like this. So this is just a normal, not a number check, because this looks funny here, but if this is a double value in Java, then it gives true if the value is not a number. And so instead of having these checks, the compiler actually does here something where it undoes a hand optimization, because on usual platforms, this code is going to perform faster. And this code can specifically also be done as a conditional move. And this is the final version of that method. As you can see here, like we took a lot of steps. There was like now 11 different steps. Some of them actually did multiple transformations at the same time. This is to show you how the compiler is just doing not just one optimization. It does like a lot of optimizations, gradually improving the graph, gradually improving the program, and then comes up with a final version that hopefully is the fastest way to write this in assembly. But it also shows specifically that last part is how dangerous hand-optimized code can be, because this manual optimization of the not a number check has to be effectively undone by the compiler. So the compiler needs to see that pattern and go back to the other version of writing this code. So this is here just shown on source code level. What can be interesting as well is to show some of this in the graph level. And what we have for this in the graph compiler is something that we call ideal graph visualizer. It's a way how you can visualize the compiler graphs, how they are transformed during the lifetime of the program. And we see here this little compiler graph. Let me just show this here. I think yes, it's good. So this is the initial version of that abstracted method that the compiler sees. As we had it here in the source code over here, we had, as I said, this is the initial version with the new object array allocation and the 2 boxes. In the compiler graph, we see a new array allocation. We see 1 boxing, another boxing. So this is the first part how the compiler sees this graph. And later you can see here it does a couple transformations where it inlines things. So we can go after phase inlining. This is now after inlining. It has now inlined this little array into this compiler graph. We can do one filter here to make sure it's a little bit nicer to read. So yes, so this is now after inlining this method. This corresponds to this piece of code here, abstracted number 3. What you see in this piece of code, by the way, is something where inside that loop, it has a type switch, where it switches on types, because based on the profile, the compiler saw that this hash code function is only called, it's a virtual call, but it's only called on doubles and integers. And the compiler will, based on this profile, create this type switch here. This profile information that is used can be very important, which is one of the reasons why using Java micro-benchmarking can sometimes lead to misleading results. Because in a normal program, this hash code function would be used from many other places as well. And then the compiler wouldn't be able to get the same quality of profiling feedback as it gets from Java micro-benchmark harness. Because Java micro-benchmark harness has actually this way where you will fork for every benchmark the JVM to get a clean state. Problem is sometimes that clean state is not what actually happens in practice. The clean state is the exception. And so something that would run very fast in this clean state, where there is no profile pollution, could run relatively slow, or like super slow, in a state of profile pollution. So this is one of the things where you need to be careful when only doing Java micro-benchmarking, that some of these results might not translate to a larger program where the profiling feedback is not as beautiful for the compiler as it is here. So the next interesting phase here is the phase of loop unrolling. So before loop unrolling, it is like this. Actually, we can see here that like one of these guards is going away. This is pretty trivial here. This was the guard that was shown on Visual Studio Code. It was shown, yes, it's this check, I think, here. So there is a guard. There's a guard where like it checks is null twice. It does the same check twice, and what happens is that like the compiler will just remove one of the checks. So this is just eliminated from the graph. In this tool, which you can, by the way, download for free from Oracle Technology Network, you can also take always a difference between 2 graphs, so you see how the compiler would transform this specific graph. I now took a difference between this version and this version. So this is before the loop unrolling. So the loop is still in there. In the loop, now we inlined the integer case and the double case. And after loop unrolling, let's see here where we are. Yes, here after, this is now the transformation number 67 on the graph. As I said here, like I was just simplifying the transformations. In reality, compiler does even more. And here, the loop is no longer here. You don't see a loop node anymore. So loop nodes are red nodes that would say loop in there. But the type switches are still here, but the loops are gone. And what happens then later is that we will have at some point a partial escape analysis. And after this partial escape analysis, the graph is super simplified because a lot of things fold. Like a lot of the code is folding at this point because we know now that we don't need this type switch anymore. We can distinguish the integer case from the double case and so on. And this is now getting pretty close to the final version of the graph. We can go a little bit lower. Let's see if we do anything else here. Well, this is the final version of the graph, how the compiler sees it before it goes to a lower level tier to create machine code out of it. So this version of the graph is now very similar, as you can see, to this version 11 of the graph. So this version 11 of the graph is represented here. The only thing that you might see is a little bit different in the compiler graph here than in the source code is that we don't have an actual if statement in there. Instead of an if statement, like this if statement is not present in the compiler graph. And this if statement is represented as this conditional node. A conditional node would select one of its input based on a condition. But here we see this double equals on the double field, which is the not a number check. And we have this conditional node that would bring in this long constant in case the value is false. This is actually not where the compiler transformations end. And this is why we have a second visualization tool called C1 visualizer. And what this does is that it will look at the graph at the even lower level. It will look at the graph with, now it looks a little bit like assembly. So we are now no longer in single static assignment form. And it is closer to assembly, but it's not yet register allocated. So you can still see that there is no registers used, specific registers used in these nodes, in these lines. And later on, it will actually do register allocation. This is how the register allocation data structure looks like, where it will now assign XMM0, a double register here, RAX here, etc. And these are life ranges of values that it needs to assign registers to. So this is also possible to look at. And then we will be at the very end, just before we create the actual assembly. This is now the low-level code that is also now with registers allocated. So now every operation has an actual register associated with it. So we see RAX in use, we see somewhere XMM0 in use, etc. And then after this transformation, the compiler will create the actual code, machine code, which is then installed in the code cache. And the machine code is no longer much different from this representation. And just to show you that like this non-abstracted version is optimized to the same thing, we can go to this objects hash raw. And this objects hash raw, which is the raw version of the method, we will see that initially it looks like this. It has like the double hash code method in there, and it's calculating the hash code. And then we will see that like after load here, this method looks exactly identical to the other method. There's no difference. Just a small layouting difference, but there's no difference here between those two versions. All right, so the question is like one of the interesting things about GraalVM is that it is written in Java itself, so you can actually look at the transformations yourself as a Java programmer, and they are quite easy to understand. So one of the transformations we can look at, let's just go here for a moment. And let's see if I have the correct version of this here up. Yes. So one of the transformation that we can look at, this is now from the source code of the Graal compiler from GitHub. And one of the transformations that I was talking about in this talk is the one where I have a multiplication node, which is a Java class. It represents a multiplication node. And the nodes have like something that's called canonical, where a node tries to replace itself with a better version of itself, right? And we have many, many of these canonical methods. And the canonical method of the multiplication has like here a special case for when the right side of the multiplication is a constant. So we have right side of the multiplication is a constant. We multiply by 31 in our example. We are greater than 0, yes. And then there is this check here where we check that the constant value minus 1, or the constant value plus 1, is a power of 2. So 31 plus 1 is 32, which is a power of 2. And in this scenario, the compiler will replace the multiplication node with a subtraction node and a left shift node. So this is the transformation I was talking about that transforms value times 31 into value shift left 5 minus value. And as you can see, there's many, many more transformations like this in the code here. And every node, every compiler node has like a ton of these transformations. So if you see a certain pattern in those compiler graphs where you say, this could actually be written better, then instead of fixing the pattern in your code, open a GitHub issue for GraalVM project, or just open a pull request, even better, and solve the transformation in a general way. Because once you did that, it will be applicable to every instance of the problem, not just your concrete program that you're optimizing. And we as compiler constructors, we really try to always find general optimization opportunities from concrete instances of where you should actually create better machine code for something. And so this is all, like GraalVM project is all on GitHub to show you like 2 of the changes I did over the last couple of days, actually on my flight here. I was fixing some bugs in the Graal compiler. And so we do some small changes sometimes, but they might have a big impact. So this was one of the changes 2 days ago where every node in the Graal compiler, every control flow node has a probability associated with it because we want to estimate how often this pass is executed. And in one of the corner cases, we would just assign a completely wrong probability on a path, which would lead to worse machine code be generated along that path. And this is the change that fixes that one. And another interesting thing is sometimes we also just reorder faces. So here is another change from last week where we found out that doing faces in a different order is giving us better performance. Because the faces are put in a certain order, but sometimes they might have dependencies on each other. And in reality, you might want to make it iterative, so kind of apply them over and over again until nothing improves anymore. But in practice, that is too compute intensive, so it makes the JIT compilation too slow. So we need to go for some kind of phase orderings. And phases and transformations on the graph are really a lot. Like in this example graph, the complex version of the graph is here transformed 185 times. Where we transform the graph into something new, or where we apply a phase on that same graph. All right, so that was the low-level part, and we are not going to get more detailed than this. Now we will go back to a more high-level view of things. But I just wanted to kind of give you a deep dive into one of these really down to the machine code level, how the compiler would work and how those transformations are applied. Because this understanding can also be sometimes important because people often ask me why don't you do this transformation? Why don't you do this optimization, right? Because sometimes people think, oh, the compiler does like this 6 different things, and then everything is good, right? In reality, the compiler has like hundreds, if not thousands, probably thousands, of optimizations in there, and we are constantly adding new ones. And it's really a game of trying to be as detailed as possible in terms of capturing patterns that you could transform. And also when you compare compilers, it's not as simple as saying like, well, this compiler supports X, this doesn't. It's really, you compare like very complex things with each other that have many small subtle differences. And doing these transformations, some of the transformations are also in a way where you're not even sure whether it's better. Sometimes you have to take an educated guess whether the new version will perform better on Intel hardware and or on AMD hardware. The reason for that is that the underlying hardware itself has sometimes not very deterministic behavior where it's hard to optimize for. This is a high-level view on performance here now. This is from one of our new benchmark suites that we have developed. This is the Renaissance benchmark suite. It has a set of workloads in there. It has quite a few Scala workloads in there. For example, Finagle workload. It has quite a few Spark workloads in there. And this is measuring here the enterprise edition of our compiler compared to the C2 compiler, and it is measuring the community edition of our compiler versus the C2 compiler in the gray bars. And what you can see here from this graph is that, well, there are some scenarios actually where the compiler choice can make a huge difference. So we have scenarios where we are 2x faster with enterprise edition compared to C2. And on average, on this benchmark suite here, we are like 32% faster. With the enterprise edition, we are 6% faster with the community edition. So, of course, benchmarks, you need to always test yourself on your program. Benchmarks only can give you an indication of this type of program with this type of behavior will give this type of performance characteristics. But generally, we want to see more benchmarks. So we want to also see benchmarks from you to be put up or provided to us because we want to test our compiler on more workloads. Every workload we can test our compiler on is a win. Because if you have optimized your compiler for too few benchmarks, it's like overfitting a machine learning algorithm. You will do very good on those benchmarks, but when then presented with an arbitrary other benchmark, you will be very bad, right? So this is why we think we need more benchmarks in the industry. We need to have more workloads in order to avoid overfitting of our compilers to specific instances of benchmarks. Yeah, there's a website for this benchmark suite. It's open source. And we're actually calling on the community as well to help us add benchmarks to this benchmark suite. For performance measurements, you can use one of the things you're always interested in is Java Flight Recorder information. Java Flight Recorder, in this case, displayed in mission control. We now have a version of Visual VM as well that can display Java Flight Recorder information. One of the things many people don't know is that Java Flight Recorder also gives you the information on compiler statistics. So when you go to the Java application tab and you look at the threads, you will also see the compiler threads. And you will see when compilation happens and how busy the compiler threads were. This is an example from compiling the Spark Scala source code with Scala C. And we can see in these workloads that the compiler threads are busy all the time, and they are still busy when the application finishes. So this is a typical application where JIT compilation has a little bit of a problem in the sense that before it even finishes its work, the program already stopped. So a lot of CPU cycles are wasted to create the optimal machine code, but in the end, it's a waste, right? It's like the program ended and the machine code is never executed. So these are scenarios where a JIT compilation can have disadvantages, so we designed in GraalVM now a version of GraalVM that can also do ahead-of-time compilation. This is just one version of GraalVM. GraalVM can do normal JIT compilation as well. So some people are sometimes confused by saying, oh, GraalVM is AOT and native image. It's one of the parts of GraalVM. It's one exciting part of GraalVM, but GraalVM can do much more and can also do just the normal JIT compilation. For the EOT compilation, when you optimize for performance, you want to optimize for various metrics. You can optimize for peak throughput. You can optimize for reduced max latency, for the packaging size of the application. You can optimize for your memory footprint, or you can optimize for your startup speed. And in the current versions of GraalVM, the situation is that the JIT version of GraalVM, it optimizes for the peak throughput. So once the application is running for a long time, it will give you the better peak performance. And it will optimize for reducing max latency because you have low latency garbage collectors available. The ahead-of-time compilation version of GraalVM does optimizations on the other spectrum, where it optimizes for startup speed, for low memory footprint, and for a smaller packaging size of your application when you create a Docker container out of it, because you can create your Docker container as a scratch Docker container. So as I said, we have two modes. One is the JIT mode in GraalVM, and for this we use the Java command in the GraalVM home directory. And the second is the EOT mode, where you use the native image command in the GraalVM directory. So currently it's like this, yes, but in the future we will actually try to optimize this further, where we are working on ways to get the ahead-of-time compiled version closer to that JIT compiled version on peak throughput and max latency. One of the interesting things about using here EOT is this is running a Micronaut example, Micronaut microservice example, and it is measuring the CPU consumption, and it is measuring the real memory usage of the process, and it gives that application 3 requests. And on the left side, you see the native image version of this application, and on the right side, you see the JIT version of this application. And what you can see is that there is a huge difference in terms of memory consumption. You see the scales are very different. On the left, it goes up to 30 megabytes. On the right, it goes up to 150 megabytes. So this is a 5x difference in terms of the memory consumption. But you can also see that the CPU consumption is very different, where on the EOT version, you really only get consumption when there is an actual request sent to that application. So there's 4 requests sent to that application. And on the right, first of all, the startup time is very long until you even can serve the first request. Here in this case, 6 seconds. And you have certain spikes of CPU, which is the JIT compiler running, which can disturb other processes that would run on that same machine. So this is really a very different profile in terms of CPU consumption and memory consumption for your microservices. One important part here is that you can tune native image specifically for small footprint. There's 2 parameters in native image which are also available in JVM, which are important for that. One is to set the max memory consumption of the application to a certain value, and the second is to set the new generation size of the garbage collector to a certain value. You can play around if you have one of these applications with these 2 numbers. Usually for a small microservice, the new generation, you can set relatively small. If it's native-based specifically, you can set it to like 16 megabytes, the new generation size. And it will determine how big the garbage collector will size this first generation where young objects are allocated into. But this is important to remember, like those 2 values are very important to look at when you want to optimize for memory footprint with the GraalVM ahead-of-time compiled mode. So this ahead-of-time compiled mode is available for many frameworks. It's available for Micronaut, it's available for Helidon, it's available for Quarkus, and we're currently working as well with the Spring team to make it work for Spring. For Spring, there's already a project on GitHub, an experimental project where you can see several Spring applications that are available for being compiled with native image. But we're still working with the Spring team to improve that. There is, for anybody who's interested in using Quarkus for these performance improvements, then there is Bert Sutter from Red Hat, who is right after this talk, actually in this room as well, that will show you from a more developer perspective, like how you use Quarkus to create then native images. And important to remember here as well is like native images is giving you the performance advantages for all of these frameworks. So it's not, there is smaller difference and depending on the workload, etc., between those frameworks. But in practice, and these numbers are also, these numbers are not a comparison between frameworks. You know, Micronaut did actually a lot of work recently to optimize their startup as well. what this slide should show you is that for all of these frameworks, native image gives you an order of magnitude improvement. And it is the native image feature of GraalVM that gives that improvement. It is not the framework that gives that improvement. The same is true for memory footprint, where also the improvement from memory footprint comes from the usage of native image, not necessarily from the framework. So you can choose any of those frameworks and profit from native image, small footprint, and fast startup. One thing in here is like, this is from a Microsoft developer advocate. A lot of you guys probably know him, Bruno Borges, previously at Oracle. He has this little tweet here, which I like very much, is that like, with GraalVM native image, and Substrate VM is the code name for native image, then you can achieve a small footprint and fast startup microservice, and you don't have to go to any other language like Go or C or Rust or some other statically compiled language, because it makes Java behave in a way that is very similar in terms of the performance characteristics with startup and footprint than those other languages. As I said, this was just the status quo, that ahead of time compilation currently is not performing as good in throughput and latency as our just-in-time compilation. Our goal is to completely close that gap over the next 12 months. And we have several optimizations in the pipeline to do that, where we will use profile-guided optimizations to achieve the same peak throughput. And we will introduce a new garbage collector into native image that is based on the G1 garbage collector and provides a lot lower latency than the current one. The current garbage collector native image only works well if you have a small amount of memory footprint. Profile-guided optimizations is one of the things we have introduced previously, but we will use it more aggressively in native image moving forward, where you can gather profiling feedback from a previous run of your application, and then feed this profiling feedback into your native image generation. You can nowadays also gather this profiling feedback not just from a native image, but you can also gather it while you run it on the hotspot, on the just-in-time compiled version of GraalVM. All right, so to summarize a couple key takeaways from this talk, these are now some key takeaways for performance tips that I think are generally applicable. Yeah, so one of the performance tips that I have for you is write small methods. The reason for that is that a lot of JIT compilers do inlining, but very little compilers do outlining. So very little compilers will ever like split up a method. It's theoretically possible, and because sometimes programmers tend to write this huge method, we are considering this as an additional optimization in the future. But it's still for a compiler pretty awkward to do that. So if you write a lot of small helper methods, you give the JIT compiler a lot of choices. If you write a huge method and inline everything in it, there is no more choice for the compiler. This is why writing small helper methods is usually good. Second general performance tip is local allocations are free, global data structures are expensive. So if you have an allocation that's only used locally, it can be completely free, like no performance overhead. It can actually be better to have it. Because it's always better for the compiler to know that a certain value is only thread local. And you store something into a locally allocated object, the compiler knows that. Third one here is don't hand optimize unless you've studied the compiler graph. An example for that would be this of a wrong hand optimization would be the one in the JDK on double to long bits, where it might have been better in like hardware like 10 years ago, but it's no longer better now. And this shows one of the problems that you have when you hand optimize something. You hand optimize for a specific target hardware, and hardware changes underneath. So it's not unlikely that like sometime into the future, when you execute on a different program, on a different hardware with different cache behavior, your hand optimization actually was the wrong one. And it can make it harder for the compiler to understand what you actually want to achieve with your program. So instead of hand optimizing your code, if you see a performance problem, create an issue, open a pull request for the GraalVM project. We are always happy to see such cases. And finally, for JIT versus AOT, for best throughput, use the GraalVM JIT compiler. We do think that the enterprise edition of our GraalVM JIT compiler is the best performance you can get for application out there. For best startup and footprint, use the GraalVM ahead-of-time compiler. And with GraalVM, you have the choice of both. Either just give me better footprint by putting the Java home directory to the GraalVM directory, or create a native image out of it. So these are the main things I would like to take you home from the talk. If this is what you remember from the talk, I think I'm very happy. So the one thing in GraalVM that I want to now, in the conclusion, talk a little bit is GraalVM has many parts, and sometimes people confuse what is like production ready right now, what is experimental right now, and what is kind of in the works but not even experimental. It's like you cannot use it at the moment. And to classify that, production ready at the moment is, of course, executing any Java JVM-based languages in just-in-time compiled mode. Production ready is to use JavaScript and Node.js with GraalVM. Production ready is also native image. It is an early adopter status due to the question of how to integrate it or whether it needs specification changes, but it is production ready for use for you. And Visual VM as well as a way to profile your application. Experimental at the moment is the Ruby implementation, the R implementation, and the LLVM toolchain that allows you to run native languages like C++ on GraalVM. And finally, we have a couple of things that we're working on for the future that are still a little bit away from being declared kind of use for experimental purposes. The one is the Python implementation. We are very heavily investing in Python, so in the future, GraalVM will support executing Python. You can currently run small programs, but not anything complex. We are focusing with Python specifically on NumPy, SciPy, and its integration with other languages, so you can then use these frameworks from any other language that runs on GraalVM. We have Visual Studio Code plugin for GraalVM in the works. We have GPU integration in a collaboration with NVIDIA. There's a project called GR-CUDA that is integrating CUDA as another truffle language into the system. We are working on a WebAssembly frontend to run WebAssembly on GraalVM as well. And we are working on an LLVM backend to support more platforms for native image. We are absolutely production ready, and we are making a difference for real workloads. One of the latest adopters of GraalVM is the Oracle Cloud Infrastructure. They are moving all of their JVM-based workloads to run on GraalVM Enterprise Edition. They have so far run like 10 million core hours without any issues, and they have seen quite some performance improvements by just dropping in the GraalVM Enterprise Edition. Here we have the OCI telemetry service. It's one of the largest services, and they get a 25% reduction in garbage collection time because we are allocating less, and they're getting a 10% improvement in throughput. So in terms of versioning, we are releasing GraalVM every 3 months continuously, and there will be the latest version of the year will become an LTS version for 1 year that you can rely on longer. Otherwise, we would actually recommend to usually stay just on the latest major branch. The next release is scheduled for mid of November, meaning about 3 weeks from now. And the major feature in that release is going to be JDK 11 support. This is scheduled for November 19th. We're working on more platforms as well in the area of ARM support and Windows support. And we're considering to add support for latest JDK as well. So then the only thing remaining for me is to tell you, download GraalVM and use it for your application. It's 100% production ready. You can get all the infos here, follow us on Twitter, and well, thank you for your attention. I hope you could get something out of the talk. Thank you very much.
Okay, thank you, Thomas. If you have any question, we have time for just one. Raise your hand, please.
Thank you. So I was saying that Graal really did 185 transformation during compilation of this small method. Don't you think that it's a little bit too crazy? How many hours this compilation took?
Okay. Yeah, so the question is, it did so many transformations, it's crazy how long the compilation takes, right? Yes. So one of these transformations can be relatively fast. So just because it does so many transformations doesn't mean that the compile time goes up by so much. Because one of the things GraalVM does is that it does the transformations very locally. So it would do just one local transformation on one part of the method. So it's not related to that. But you are right that we as just-in-time compiler developers need to be always aware of not introducing too many heavyweight transformations that would slow down the just-in-time compilation process too much. Because for us, any CPU cycle we are spending on compilation is a CPU cycle that we are wasting on your server, right? We are using from your server. So GraalVM generally is a very fast compiler if you compare it with traditional just-in-time, with traditional compilers like LLVM, for example, or even if you compare it with C2, our compilation speed in terms of compiled bytecodes per second is faster. Because we avoid very heavyweight transformations, specifically in the lower level parts of GraalVM, like the register allocator, is where we do less heavyweight transformations. But you're totally right that, like, for us, it's always a balance act between adding another optimization here versus and making the machine code faster versus making the compilation time slower. And this is why for every change that goes into GraalVM, we do very extensive testing on about 6-7 benchmark suites, about 100+ individual benchmarks, where we test not only the impact of peak performance on that benchmark, but we also test the impact on compilation time on that benchmark. Thank you for your question. Yes, I think we are kind of out of time, but we will have a discussion zone right afterwards, and I will be there and answer all your detailed questions with pleasure. Thank you very much.